In this video, I'm going to start talking about stoichiometry. So stoichiometry is essentially just predicting how much of a product we can get given a certain amount of reactant. And the reason this works is because of the law of conservation of mass, which tells us that during the reaction we can't create or destroy any matter. And so for instance, if we have this reaction here where we're taking 2 silver plus 1 sulfur and making it silver sulfide, we start with the reactants, the silver and the sulfur, and make our silver sulfide. That means if we have 2 atoms of silver and 1 atom of sulfur, we make our silver sulfide. Similarly, if we have 2 moles of silver atoms and 1 mole of sulfur atoms, we make 1 mole of our silver sulfide. And so that's why we need this mole to mole ratio for it. And that also means that if we start with a certain mass of the silver and a certain mass of the sulfur, we will get the same mass of the silver sulfide. We can't create or destroy mass. And so we can use this fact to actually predict how much of a product we will get given a certain amount of reactants. And so this information provides us with the mole-to-mole factors that convert between the moles of the different compounds in the reaction. And so the equalities derived from this equation are this: that 2 moles of silver will give us 1 mole of sulfur, and so we can use that to predict how much of the sulfur will react given how much silver we have, and vice versa. And 2 moles of silver gives us 1 mole of the silver sulfide, and 1 mole of the sulfur gives us 1 mole of the silver sulfide. And so we can use all those mole-to-mole factors to actually predict how much of one we will make or use given any of the other ones. So the number of moles of each compound matches the number of moles in the balanced chemical equation. So again, this is why it's very important that we have a balanced chemical equation. And so we want to know what the mole-to-mole conversion factors are. We can look at a couple reactions here. So we already saw with our silver and sulfur that we have 1 mole of the silver sulfide to 2 moles of silver, 1 mole of silver sulfide to 1 mole of sulfur, and 2 moles of silver to 1 mole of sulfur. But we can do this for any reaction. So for instance, we have this iron plus sulfur becoming iron 3 sulfide. So that means we have 1 mole of the iron 3 sulfide to 2 moles of iron. We have 1 mole of iron 3 sulfide to 3 moles of sulfur, and 2 moles of iron to 3 moles of sulfur. And of course, with any of these conversion factors, you can flip them as well. And so if you need to cancel out the units that are on the top, you can just flip it, and those would also be conversion factors that you can use. And we can use these mole-to-mole factors to convert between the moles of one compound in the equation and moles of another. So again, if we use our example here of the 2 silver plus 1 sulfur becoming silver sulfide, in the chemical reaction of silver and sulfur, how many moles of product are produced from 1.42 moles of sulfur? And so to do that, we use this. So the 1.42 moles of sulfur will cancel out with the 1 mole of sulfur on the bottom, and we are left with the moles of the silver sulfide. And this is just a 1-to-1, so we will end up with the same number of moles of the silver sulfide as we had of the moles of sulfur. And now if we want to use the same reaction to guess how many moles of the product are produced from 1.42 moles of the silver, now we have to use this mole-to-mole ratio right here. So 1.42 moles of silver to 1 mole of silver sulfide to 2 moles of silver, and so that will give us 0.710 moles of the silver sulfide in this case. When we do these stoichiometric calculations, we are going to follow a general scheme that we can look at as a flowchart here. So we will start with the mass of compound A. So if we have some reaction of A becoming B, we start with the mass of compound A, and we can use the molar mass of A to then get to the moles of compound A. Then from there, we can use the mole-to-mole ratio of A to B to get to the moles of compound B. Then we can use the molar mass of B to go from moles of compound B to mass of compound B. And so this is the general scheme that we will be following in a lot of these calculations. If we want to look at this in terms of the units that we'll be using, we start with our mass of A. We will use the molar mass of A like this to cancel out the grams of A and get to moles of A. Then we use the mole-to-mole ratio of A to B. Then we use the molar mass of B. So this is our given mass here of A. This is our molar mass of A, our molar ratio of B to A, and our molar mass of B. So the mass of A will cancel out, the moles of A will cancel out, and the moles of B will cancel out, and we are left with just the mass of B. So we can see how we can go from the mass of A to the mass of B. And now let's look at a few examples of this. So in this first one here, we have sodium reacting with oxygen to produce sodium oxide. We want to know how many grams of the sodium oxide are produced when 57.5 grams of sodium react. So the first step that we always want to do with these is come up with a balanced chemical equation. Then we can use the mole to mole ratios in our balanced chemical equation. So this is our given mass here. This is our mass of A essentially. This is our given mass. Then we want to use the molar mass of sodium here. Then we use our mole to mole ratio of sodium to sodium oxide. Then we use the molar mass of the sodium oxide. And we see that this will give us 77.5 grams of the sodium oxide. So what this is telling us is that if we react 57.5 grams of the sodium with an excess amount of oxygen, that we will end up making 77.5 grams of the sodium oxide. In the next one, we have lead 2 sulfide reacting with oxygen gas to produce lead 2 oxide and sulfur dioxide gas. We want to know how many grams of the sulfur dioxide can be produced when 15.0 grams of oxygen reacts. So again, the first thing we want to do, come up with our balanced chemical equation, because remember, this is what we use for the mole to mole ratios. This is our given mass of oxygen right here, the 15.0 grams of O2. Then we want to use the molar mass here of our oxygen. So remember, this is O2, so we have to take the 16 that you would see on the periodic table and multiply that by 2. So that's the 32.0 grams of O2. Then we want to use our molar ratio of the oxygen to the sulfur dioxide here, then the molar mass of the sulfur dioxide. And when we do that, we get 20.0 grams of sulfur dioxide. So again, what we're saying is that if we react 15.0 grams of O2 gas with an excess amount of lead 2 sulfide, what we would get is 20.0 grams of sulfur dioxide. And of course, we could do this calculation again if we wanted to find out how much of the lead 2 oxide we were doing, but we would want to use the mole to mole ratio of the oxygen to lead 2 oxide and the molar mass of the lead 2 oxide. But we can go from any one of the things in this equation to any of the other things and find out, say, how much of any of the two products we would make, or find out how much of the other reactant that we would react with. And so let's look at how we can do that using this equation right here. So in the first one, we want to know how many grams of the copper 2 phosphate are produced when 3.70 grams of the copper 2 chloride react. And so in this one, we start with our given mass again. We multiply that by the molar mass of our copper 2 chloride, then the mole to mole ratio of copper 2 chloride to copper 2 phosphate, and then the molar mass of the copper 2 phosphate. And what we see is that we get 3.49 grams of the copper 2 phosphate. But then if we look at how much of the copper 2 phosphate we would produce if we instead use 3.70 grams of the ammonium phosphate. Now again, we want to start with our given mass of the ammonium phosphate, then the molar mass of ammonium phosphate, then the mole to mole ratio of ammonium phosphate to copper 2 phosphate, and then the molar mass of copper 2 phosphate. And that gives us 4.72 grams of the copper 2 phosphate. And you'll notice that we get a different amount for each one of these. So we're using the same mass, but we're looking at it for the two different reactants. So if we use 3.70 grams of the ammonium phosphate, we would get 4.72 grams of the copper 2 phosphate. But we saw before that if instead we used 3.70 grams of the copper 2 chloride, we would only get 3.49 grams of the copper 2 phosphate. And we'll see in future videos that that is important, which one will give us fewer amounts of the product. But now what we can do is actually find out how many grams of the ammonium phosphate are used when 3.70 grams of the copper 2 chloride are reacted with an excess amount of ammonium phosphate. So we're saying that we have only 3.70 grams of copper 2 chloride, but we can have as much of the ammonium phosphate as we want. But we want to know how much of the ammonium phosphate will actually be reacted in this reaction. And so again, we start with our given mass here. We use the molar mass of the copper 2 chloride, then the mole to mole ratio of the copper 2 chloride now to the ammonium phosphate. And then we use the molar mass of the ammonium phosphate. And what we find is that this is 2.73 grams of ammonium phosphate. meaning that if we react 3.70 grams of the copper 2 chloride, that this would use up 2.73 grams of the ammonium phosphate. And so we can use the mass of one of the reactants to find out what mass of the other reactant would actually react in this reaction. Another important consideration here is that almost every chemical reaction involves either a gain or loss of energy. So the heat of a reaction is the amount of heat absorbed or released during a chemical reaction. When it's released, it's called exothermic, such as the combustion of methane. And when heat is absorbed by the reaction, this is endothermic. And this is what cold packs, for instance, use. Where if we have an endothermic reaction, the sign of the heat, the delta H or Q, either of those will work in a class like this. The sign is positive. If it's exothermic, then the sign is negative. But what we see is that we can also use the heat like they are a reactant or product in our reaction. So if it's endothermic, we put it on the reactant side, exothermic on the product side. What we mean by that is we can put it like this. This is our combustion of methane gas. We see we have the heat in the product side, so this is exothermic. We can think about it this way. We're taking our two reactants here, we're putting them together in a reaction, then we are getting these products out. And it's releasing heat from this reaction, so we can think of the heat as a product of this reaction. But if we have an endothermic, we see that we now have the heat on the reactant side. And so we can think about it this way. We're taking our reactant plus heat, we're putting them together into a reaction, and then we're getting the products out. So we have to put energy into the reaction in order to get the products out. And that's why in endothermic reactions we can think of the energy as being a reactant in it. And so this is what it looks like for both of them. If we have exothermic, the heat is a product. If it's endothermic, the heat is a reactant. And you'll notice that we have plus on all of these in our chemical reaction. So we said earlier that in exothermic we would use the sign as negative, in endothermic we would use the sign as positive. But that's if we are just talking about the heat in a mathematical sense. When we're looking at it in a chemical equation like this, you want to think of the pluses as almost being more like the word and. So for instance, with the combustion of methane, it's like we have methane and oxygen becoming carbon dioxide and water and heat. Or in the endothermic one down here, we have heat and calcium carbonate becoming calcium oxide and carbon dioxide. So you don't want to think of those pluses in a mathematical sense, but more in a conjunctive sense. But when we do get to math using these numbers, then we do want to actually make sure that we have these signs on them. So how much heat in kilojoules is released when nitrogen and hydrogen react to form 50.0 grams of ammonia. The heat of this reaction is minus 92.2 kilojoules, and so that would be a reaction that looks like this. Because this is exothermic, we want to put our heat on the product side here. And so we can use this conversion factor that 2 moles of ammonia made is equal to the 92.2 kilojoules released. And so we start with our given mass here. We use the molar mass to convert it to moles. Then we use this conversion factor right here, that we have minus 92.2 kilojoules per 2 moles of ammonia. So we see in this case we do want to make sure that we have the correct sign on the heat released right here. And so this would give us minus 135 kilojoules. So what this is saying is that if we make 50.0 grams of ammonia from this reaction, that this would release minus 135 kilojoules of heat. Then if we look at this for the combustion of butane, this will release minus 2,877.3 kilojoules per mole. We want to know how much heat is released when 33.3 grams of carbon dioxide are formed. So again, we want to get our balanced chemical equation, where again, this is exothermic, so our heat is in the products. We can use this conversion factor here, where we have 8 carbon dioxide moles produced for every minus 2,877.3 kilojoules. And so if we are making 33.3 grams of carbon dioxide, we want to start with this, then use the molar mass of carbon dioxide, and then we use this conversion factor here, where it's minus 2,877.3 kilojoules per 8 moles of carbon dioxide, and this gives us minus 272 kilojoules released from this reaction. But anyway, that was everything I wanted to talk about in this video. I hope you found that helpful, and I will see you in the next one.